Hello and welcome to the AICE Chemistry lecture series. In this video today, we're going to start chapter 12 of the AICE Chemistry book, which goes over group 17 element, or the halogens, essentially. So this chapter is all about inorganic chemistry and the reactions and properties of those halogens. There are a total of 4 sections in this chapter. Section 1, which we're going to go over in this video, goes over the physical properties of the group 17 elements. And you are actually going to need to know more than you think. You will need to be able to look not just at the reactions of these elements, but what do they look like, what states of matter do they have, etc., etc. Group 17 elements in section 2, we're going to look at their reactions. And then we're going to go into specifics. For example, in section 3, we'll look at the reactions of the halide ions specifically, so not the halogens, but their ions. And in section 4, we'll go over a specific type of reaction, which is disproportionation. So let's get started with section 1. Section 1, like I mentioned, is going to go over the physical properties of group 17 elements. So we're going to be looking at not the reactions yet, but things like the electron configuration, the state of matter, their colors, so on and so forth. Halogen atoms, the group 17 elements, are going to all have very unique electron configurations. Every single halogen has 7 valence electrons. So fluorine has 7 valence electrons in energy level 2, which we can see here. Let me use a different color here. So we can see here how fluorine has 7 valence electrons in energy level 2, which is valence shell. Chlorine has 7 valence electrons in its third energy level, which is its valence shell. Bromine has 7 valence electrons in the fourth energy level, which is its valence shell. And then finally, iodine has 7 valence electrons in its fifth energy level. I will mention that astatine, which is not shown here, is also technically a halogen, but it is not directly part of the curriculum. However, you might still be asked about astatine on the AS exam. What you need to realize is that everything that applies to these elements right here will apply to astatine because it's still a halogen and it still follows the trend. So if we had astatine here, which its symbol is AT, the electron configuration would be very similar, meaning that you will still have 7 valence electrons. It will just be on the next energy level up. So the very end of the astatine electron configuration would end in 6s2 5p5. So you still have those 7 valence, sorry, not 5p5, 7p5, 6p5. Oops, let me correct that. So that's going to be 6p5. So you will still have those 7 valence electrons because it is technically a halogen. It will just be higher up. You are essentially asked to not know this right away, but be able to follow this trend of the halogen electron configurations to know the electron configuration of astatine. So all halogens are going to be nonmetals that lose 1 electron when they react ionically. Whenever a nonmetal reacts with a metal, usually, will lose electrons in that reaction. And in the case of the halogens, it will be 1 electron becoming an ion of -1 charge, which is our charge of the halogens in ionic compounds. At room temperature and pressure, though, all the halogens are diatomic molecules, which are going to be covalently bonded to themselves. So we can have 2 sides to halogens. When they're in molecule form by themselves, we're going to have a diatomic molecule. So F2, Cl2, Br2, I2, even AT2 if we're talking about astatine. So this is when they're by themselves in their elemental form, in their molecule form. All of the halogens are diatomic. When it comes to ionic compounds or anionic compounds, Oops, I'm writing not so great here. Nick. So when it comes to ionic compounds or in ions, the halogens are only a -1 charge. So fluorine will be F minus, chlorine will be Cl minus, bromine will be Br minus, and iodine will be I minus. So when we have a compound like sodium chloride, for example, an ACl, this sodium chloride is made of the sodium ion, Na+, and the chloride ion, which is Cl minus. So in any ionic compound, there will be -1. In a molecule, they'll be by themselves. In a molecule, they'll be diatomic. So let's keep going. We can see that more clearly here. And these are all the different properties, physical properties of the halogens that you should keep in mind. Fluorine, chlorine, bromine, and iodine, like we say, are the halogens. Astatine as well, even though they're not directly in your curriculum, you should still be able to follow the trend. So a few things that we can see. All of them are going to be diatomic when it comes to the element by itself, like we just mentioned. So there's just going to be two atoms of the same element bonded together. As you can see, as we go down that group, though, notice the pattern. Notice what happens visually. They get larger and larger and larger. And we're going to talk about this in a second because this size does influence a lot of the properties of the halogens and the halogen diatomic molecules. Like I said earlier, their common charge is -1. There are polyatomic ions that include a lot of these elements, like chlorine and bromine and iodine. But by themselves, their charges are always -1. Now let's talk about their physical properties because these are important. You do need to know this. You do need to have these memorized. Fluorine. The fluorine diatomic molecule, fluorine gas as an element, is a gas in standard temperature and pressure and even room temperature and pressure. It is pale yellow in color. Remember this. You will be asked about the color and state of matter of elemental fluorine. Chlorine, also a gas at room temperature. But that gas is going to be a greenish yellow color instead of that pale yellow for fluorine. Again, these colors are really hard to see because they're pale, and so they do need a higher amount of concentration of the gas for you to see them. Bromine, on the other hand, is a liquid. No longer do we have a gas. Once we get to bromine, we now have a red-brown liquid that gives off a red-brown gas because this is very volatile. And we'll get to the volatility in a second. Iodine is going to be a grayish-black solid that gives off a purple vapor. So iodine is normally solid at room temperature and pressure. It is a grayish-black solid, but it does very easily turn into a gas, which is a purple color. So be very careful when you're being asked about the difference between solid iodine and iodine vapor. Solid iodine is grayish black, iodine vapor is purple. And then astatine is a dark metallic color. It is a solid. It is also radioactive. So it is something that is really hard to study because it decomposes really quickly. It undergoes radioactive decomposition. Or the radioactive decay is another way to say that. So remember the color of the four main halogens. Remember, they state of matter. These are the melting points and boiling point, just to show you that they're very low. The boiling point of fluorine is -188 Celsius, meaning that it's going to be a gas at room temperature and pressure, like chlorine, which is a more modest -35 degrees Celsius boiling point. Once we get to bromine, notice how the boiling point does increase, and so does the melting point. That boiling point for bromine is 59. Sorry, the boiling point is 59 degrees Celsius, meaning it's above room temperature, but its melting point is below it. That's why bromine is a liquid at room temperature, because room temperature falls right between the two boiling points and melting points. So room temp for bromine is right here, which is why bromine is a liquid at room temperature. It has melted, but it has not boiled. On the other hand, room temp for both fluorine, and chlorine is above their boiling point, meaning it has both melted and boiled. That's why they're gases at room temperature. However, for iodine, the melting point of iodine is 114 degrees Celsius and its boiling point is 184. And this is with a grain of salt, because actually iodine at room pressure doesn't usually boil or melt. It'll sublime, meaning go straight from the solid to the gas. But notice how the melting point of iodine is above room temperature. I mean, room temperature is down here. So it hasn't even melted yet. So that's why iodine is a solid at room temperature. So that's where these states of matter come from. The fact that room temperatures are going to be above the boiling point for fluorine and chlorine, between the melting and boiling point for bromine, and below the melting point for iodine. Now let's talk about why this happens, because this is very important. So you don't need to just know what the states of matter are and the colors, but be able to explain why this happens. So moving on. So halogen molecules. Halogen, like we said, are diatomic molecules at room temperature, and so they have varying physical properties. One of the biggest ones is their volatility. Volatility, if we have not used this word before, I'm not sure if we have or not, is the ease with which a substance evaporates. Saying something's highly volatile or saying something's volatile means that it evaporates at a low temperature. So whereas if we say something is not volatile, it means that it will evaporate at a high temperature. So it will boil at a high temperature. So halogens are all going to have increasing melting points, like we saw in this here. So you can see how the melting point goes up as we go down the group, from negative 220 to negative 101, negative 7 to 114. So they have increasing melting points and increasing boiling points as well, meaning their volatility decreases as you go down the group. You have to be careful with these two words. Boiling point and volatility are opposites in trend. Boiling point is how high the temperature needs to be for it to boil. Volatility is how easily it boils, meaning that the higher the boiling point, the lower the volatility, because the higher the boiling point is, the less likely something is to boil or to evaporate. So as we go down the groups, these get less volatile, meaning that they melting points go down, their boiling points go the melting points go up, the boiling points go up, meaning they're less likely to evaporate and less likely to be gases. That's why if we look at the state of matter, we go from gases to liquids to solids. This is mainly due to the London dispersion forces that hold these molecules together. We know that if two atoms bond to each other, they're of the same element, like in these molecules, these diatomic molecules, then we're going to have non-polar molecules. They have to be non-polar because the electronegativity is the same. When we have two, for example, chlorine, we'll put chlorine because it's like the most common one. When we have two chlorine molecules bonded together, the electronegativity of chlorine is going to be the same in both sides. I believe it's 3.0. So because both of these chlorines have the exact same electronegativity, 3.0, then this is a non-polar molecule. Because it's a non-polar molecule, the only force of attraction between molecules of chlorine is going to be London dispersion forces. And we talked about this before already. We talked about London dispersion forces and what makes London dispersion forces stronger. Remember, the bigger the size and the flatter the molecule, the stronger the London dispersion forces. Well, flatness here doesn't really count because we only got two atoms, but size does as we go down. As we go down the group, the size of the halogens change. The larger the halogen atom is, the stronger the force of attractions become. So as we go down this group, these atoms are getting larger. Let me make that a little smaller. So as we go from fluorine, chlorine, bromine, and iodine, these become larger down the group. And so their London dispersion forces become stronger down the group. Stronger London dispersion forces means, let me use a different color there. Stronger, more London dispersion forces means larger melting points and boiling points because they're both affected by London dispersion forces. Only because these are covalently. And so that means that we go from gases to liquids to solids as we go through the halogens. So be able to explain this is very important for you to understand that the size of the molecules is going to play a part because these are nonpolar. The size of the atoms means that the larger the atom, the stronger the London dispersion forces, and the stronger the London dispersion forces, the stronger or higher the boiling points, which is why they become less volatile than the group, and so they go from gas to liquid to solid. You might have to explain that in a paper 2 question, and those are usually worth around 3 points when we explain that. So this is a visual representation of that fact that we just talked about, right? When we have chlorine or iodine molecules, right? Chlorine is a gas at room temperature because the chlorine molecule is the chlorine atoms, are much smaller than the iodine atoms. The chlorine atoms being smaller than the iodine atoms means that their forces of attraction, those London dispersion forces that happen because of those temporary and induced dipoles, are going to become weaker. Small molecules means weaker, short-lived London dispersion forces, and so those are much easier to break, and so these chlorine molecules are more free to kind of move away from each other. Iodine, on the other hand, is a solid. Why? Because the iodine molecule is larger. The iodine atoms are larger. And this is not a double bond, by the way, just a single bond. It's just shown a little weird. They have strong, persistent London dispersion forces because of that larger size. And so they're going to be harder to break, keeping that iodine as a solid. Now, this is something I wanted to show you and make sure that you understand. When iodine is a solid, that solid is not random. There is still a lattice structure to the iodine solid. There is a structure just like ionic and metallic solids have, but the difference is that instead of having atoms or ions at these vertices, we have iodine molecules at the vertices of that lattice, at that solid. So you can see that here very well, where we have the iodine molecules kind of connected to each other with London dispersion forces, and so it becomes a lattice. So all solids, whether they're molecular, ionic, metallic, are going to have a lattice structure, and iodine is no different here. Iodine does have the lattice structure. It is held together though by London dispersion forces because they're persistent, are strong because of the large size of the iodine. All right. Now that's it for physical properties of the halogens. Make sure that you remember all of these, and mostly make sure you're able to explain this right here. Be able to explain from the atomic size that as the halogens go down the group, the atoms of the halogens get larger, which means that their London dispersion forces, because they're nonpolar, are going to get stronger because London dispersion forces get stronger with size and number of electrons. As the London dispersion forces are stronger, their melting point and boiling points go up because it's harder to break those intermolecular forces. And so in the state of matter, they go from gas to liquid to solid. And also be able to remember the colors of these. All right. Well, that's it for section 1 of chapter 12. I'll see you all in the next chapter next section, next video to go over section